So we are bringing you a story about the new liquid library AnyLogic has. And the one application we want to talk about is in oil and gas, precisely in upstream. And it's a Canadian story. Why Canadian? Because the oil sands is 97% of the Canadian reserves. Why does it matter? Canada is the third largest proven country to have oil reserves in the world. So a lot of the reserves are in oil sands. Oil sands are tricky. I'm going to explain what in situ is in a moment, so bear with me. What you can take from this slide is it's really expensive, and it's a very young technology. A lot of capital-intensive money when you build the facility, but also to run it. It's very expensive, which means right now they're in big trouble because the oil price is down. Hence, they need help. So let me explain a bit what in situ oil production is all about, and I explain a bit more the business challenges that are there, and there are actually plenty. I'm only going to pick one example, otherwise I'm going to confuse you. And then Alvaro will talk more about how we are taking that complex challenge into models and help the industry. So what's in situ? What's oil sands? Oil sands, if you look at the right, it's a mixture of sands surrounded by water molecules and around it oil. And this oil is very, very sticky. If it's at normal temperature, it's like asphalt. You can walk on it. And Canada is not the only country to have it. Venezuela and Russia have it as well, but Canada is the most advanced in this technology. So what's the trick of getting this oil out of the earth? Well, for 80% of the reservoirs which are deep down in the earth, the trick is heat up. Heat up, which means you bring the viscosity of the oil down, and now it's pumpable. How do you do the heat up? You inject wells deep down into the earth, inject steam, and through the steam you bring energy in and heat up your earth and achieve exactly that. And one of the two technologies to do it, I'm only going to talk about one, which is the steam-assisted gravity drainage, or SAGD. So how does such a facility look like? Well, it's a vast system of lots of feedback loops. Let me talk you through it for a moment. Picture this, you have a huge acreage, and in this acreage you have the wells. Now these wells are clustered together in pads, and then from those pads and to those pads you have a lot of pipes running. Why? Because steam production is very expensive. So you want to optimize your capital by having a centralized unit to deal with all the steam and all the oil that's coming back out of the ground, but then you need to distribute it and cover the whole reserve. So it's like a huge distribution system, steam in, and what comes back out of the well is a mixture of oil, gas, water, as well as a bit of sand and some salts. So it's kind of how do you optimize the capital? So lots of stuff running around. Now, this is where the liquid library come in. Picture this. Assume its operation. You have issues with a well. It could be planned, it could be unplanned. So now a well is down, it cannot take steam in. What's the consequence? Now you don't want to turn down the steam generator because that's expensive. So the question is, what do you do? Where do you put the steam? You have all these other wells out there, and it could easily be over 100 wells in a well-developed field. Where do you put it? To answer that question, if you now have information about the reservoir, how it will respond to different quality and steam flow, now you can run simulation to answer that question. Does anything like that exist right now in oil and gas? No, it doesn't. How does oil and gas handle this problem at the moment? Mega spreadsheets. What is one of the challenges of spreadsheet? Everything is there at the same time. So that's another challenge why it is so complicated, the system. They assume when the reverse happens, like the steam generator gets down, you have immediate effect at the well. That's not going to happen. There is a flow. There is a time lag before something happens. And there's also a time lag in the reservoir. And just to make matters worse, each well behaves differently and is rather unpredictable in comparison to conventional oil. So what does it mean? Lots of headaches for the people who operate it. As a rule of thumb, there's about one production engineer can handle about 15 to 20 wells. That's all they can handle in the spreadsheets right now. So lots of challenges, lots of opportunities actually through the whole asset cycle, but we are only going to talk about one. And Alvaro is explaining a bit more how we're handling this.
Thank you. So, is that okay? Yeah. So how do we model this, and how do we deal with this issue? So going back to the previous picture, each one of these elements of the system is actually a big challenge per se. So just the CPF, the Central Processing Facility, involves lots of challenges and lots of complexities. And at the same time, the reservoir and the wells. So we have developed different simulation models, each one of them representing each one of the components of this system. So at the end, we end up with a huge system that can connect each one of those simulation systems, and we can drive the system from one or another side. So from the CPF perspective, we can decide to manage and model the CPF and see how the wells and pads will behave based on the decisions that we're taking. And vice versa, we can model from the reservoir all the wells, or we can integrate and plug all these simulation models at the same time and take decisions in real time. Besides that, we have lots of external sources. We have operational data. This operational data might be the behavior and the operational time of each one of the activities. So that information can be real-time information or can be historic information that can be modeled and plugged into the model. We have production profiles that can tell us from each one of the components of the emulsion, when are we receiving, how much are we receiving, and based on each one of the factors that we have in the model. And at the same time, we have Excel files and TXT files. And all of them are combined, and the model can identify when we have a lack of information and can auto-generate information in order to cope or to fill whenever we have a hole of information, a lack of information to deal with this. So basically, each one of these micro-models or individual models is a combination of agent-based and discrete event simulation. But on the top of that, we have the fluids library. So what the fluids library is doing, and this is why AnyLogic was a huge and enormous tool for us, is that it allows us to integrate and communicate and manage the lag between each one of the components of the models. So imagine this situation. What Birgit was explaining, when you have a break in a pipeline, or you may have a break in a valve, or you may have a break in a well, you have some time in order to affect whatever is following the sequence, right? So when you have this, when you're trying to model this with a spreadsheets, this is quite difficult to model. But when you're including the fluids library, you have a full steady state model where imagine strings that are connected. So the movement or the minimum affectation in one corner of the model eventually will be affecting other components of the model. So this was a huge advantage, and this was why AnyLogic was really important for us. So, and besides that, we integrate this with external sources, as I already explained it, and we also incorporate external Java libraries, which allow us to increase the computational calculations inside the model. So we can add physics, chemistry, and many other things that are really important to model these situations in real life. So a single model, imagine this situation, may have around 120 wells, just a single, and each one of them is an individual agent. So from the complexity model, and when Berger was saying that companies outside use spreadsheets, one modeler, by using spreadsheets, may model probably 10, 20 wells. But a real case may have around 120, and sometimes they have hundreds, 200, 300 wells in a single field. So it's really complex doing this through a different way other than simulation. So when we use simulation, we can easily put 120, 200, 300 wells. We can model different behaviors. Each one of them use something called curves, and curves are production profiles that comes from external files or, as I said, from auto-generated information. And then you have several parameters and several variables that are affected all over the time. So when is this affected? This happens every minute. They are dynamically affected. But in terms of general, and they have different granularity levels. So some of them are affected every 24 hours, I mean daily, or some of them are affected every minute. And depending on which model is driving the full system, we define the granularity of the full simulation. Then another really complex aspect of this is the mergers. So when we are merging, and this is why managing this through spreadsheets is really complex, when we are dealing with spreadsheets to deal with each one of the elements, and we want to plug them together, we don't know exactly how to manage the proportion of the production or how to manage the steam going to the wells. Using mergers is quite simple. It's just plug and play, right? But there's a lot of calculations inside this. But we can see on real time how one decision is affecting through all the system. And we have many other components like pipelines, like mergers, like valves, like sources and exits. So all these are spread through all the simulation. So since this has several levels of granularity and several levels that we can go deep to see the operation in real time, or we can go really up to see the planning. So you can see a few dashboards here, where you can actually build dashboards to see the operation in a really high level and to see what is happening at each one of the pads and wells. And you can have actually like indicators to see, oh, are we doing right here? Or you can actually dig inside till you get to the source of the problem and take decisions in real time. Or you can actually go and see basic dashboards, based on the financial status, and you want to take decisions from the CapEx perspective. Or you can go to the central processing facility and take decisions in the operations in real time and see how the configurations in many components inside the CPF are affecting the full production of the full field. So this is one example that we are seeing here, right? So what are the advantages of this approach? First of all, we have dynamic populations. So we can have 2 wells, we can have 200 wells, and still we can see the results in real time in a very fast performance results. We are using fluid modeling. So this fluid modeling, as I said, is having a full ripple effect, and it's affecting what is happening one side of the model. Eventually will affect many other components. Low steam, less production, and you want to see how and take decisions in real time. You can track all the batches in the model. So you can track what is happening every minute, every second, and hence you can track the quality. And in the oil and gas industry, quality is really important, not only from the input, but for the output, because based on that is the profit of the company. So these type of models allows us to manage individual agents which tracks the quality at every moment and at every corner of the model. And then we can manage many other decision algorithms. So as I said, since they have different models and different problems, you can deal with scheduling problems, or sequencing problems, or reliability, or maintenance. And you can see when the variability increases, what will be the affectations in a single well or in the full system. And then you can start creating individual decision algorithms that leads you at the end to an optimization routine. So at this moment, we are already incorporating these algorithms to find which are the best decisions in long terms and short terms for companies. And finally, you can do multiple scenario analysis. So as someone before said, using Monte Carlo is really important. And then, yes, we use Monte Carlo to include one single dimension of variability, or sometimes we're just analyzing a full range of variability, and we run for hours to see where we can have the best possibility of the models based on what is happening currently on the field, or what is happening, or what actually is forecast to happen in the future. So many things are happening here, and many disciplines are involved in this. Actually, in order to deal with this, we had to work in a research team, and it was a multidisciplinary team that includes people from petroleum engineering, from industrial engineering, and many other fields, in order to understand each one of the dimensions of the problem that we might have to deal with in order to solve this problem. So I'm going to hand off the word to my colleague.
Thank you. So where are we going from here? Now we have built a base model that allows a system approach, and that is one of the big differentiators. So far, for SACD, there were all isolated little pockets that used simulation. This approach allows it to tie it all together, to close the loop between what happens above the ground and what happens below the ground. We can now conquer the complexity that goes with it, and the scenario management helps with this approach as well, because now we can do what if. And the fluid library helps with all the ripple effects, and we mentioned just one or two, there are a lot more. So just picture you lose a pump, and now where do you go with all the water? What happens? It is an immediate ripple effect, but people need to take decisions and have choices. Which choices are the best to take? So there's lots more to come. This is just a teaser where we are going, but we're super excited, and we think there's a lot that's going to happen. We just definitely got a lot of interest in the industry, and as Alvaro mentioned, this was possible because we tied different disciplines together, including industry partners as well as people from simulation experts, industry expert, operational experts to achieve this. And now we're taking questions. Thank you.
Hello, thanks for your presentation. Is it, now you've said you've used it as a discrete event model so far, but you don't use any
No,
the dynamic library?
It's all in it.
It's all agent?
It's all in. Agent-based, discrete event, and dynamics, all combined.
Oh, all combined?
All combined.
Okay, because I thought I just heard one part. Which part, I'm sorry. It's in an experimental phase, and you have a lot of multidisciplinary group working with you. Where do you, and the company is looking to reduce costs. How do you think this will work in that regard? Okay,
I'll give you a few examples, just a few ideas. As I said, CapEx is very expensive. About 60% of the CapEx of SACD is locked in at the time they start operation. And that money sits in the first wells and well pads as well in a central processing facility. Now, when they start up, these wells have a production profile, so they have a lifetime. Hence, even if they, when they start, at a certain point, the wells are not productive anymore, and you need to start opening up new pads. The decision at what point can you add a new pad and still have enough capacity in a central processing facility to add helps you with working capital. Because adding a new pad is, again, lots of millions. So that's one angle. The other angle is see the responses of all these hundreds of wells coming back, and they still need to fit into central processing facilities. A generator needs to be taken out of production ever so often to be cleaned. So when you schedule that taking out and aligning other maintenance with it, there's an optimization in energy. There's so many areas where you can make money in here, and if you just save 1%, then you pay the entire overhead of that individual company for at least a year. Well, 1% would actually give you even more.
With respect to the production curves, here, you had mentioned that you had a set of curves. Did you use dynamic curves, or did you use those half a dozen and then you chose the right ones, or was it some sort of a hybrid where there were some parameters involved? And based on what you chose, did you see any constraints in how those could be applied in the model?
Okay, there are two possibilities, or actually three. The model can be fed based only on external curves. When you're just reading external curves, they are not as dynamic as we want, right? So they are just a slope during the time that tells you what is going to be your production all of the time, but you don't have a what-if analysis there. But when you're using the second or the third approach, which is internal calculations or simply a hybrid approach where you're using curves and you're also adding some other variabilities factors, yes, you can actually see through the time how the curves behaves and how the production is affected based on some specific stimulus. So when you change, when you inject more steam, when the quality of your steam is reduced and so on, you can see how that affect your curve production. And now, based on what are the most important factors, well, I have to tell you that there are several of them. And there are internal quality parameters as well as even weather parameters that affect the production. So, and depending how you are driving the model and who drives the models, from which aspect you are trying to analyze a specific problematic, you can actually identify specific factors and key parameters that you say, I need to concentrate on this. But this is why the systemic approach is very important, because you may probably take decisions based on some parameters, but then you can go one level up and reevaluate your full scenario and say, oh yeah, but this other aspect is really important, so I need to balance both, and then take decisions from the company perspective.
Hi, I'm curious to kind of follow up on that question. Have you had a chance to look at how your approach or model can actually fit the data, like how good the model fit? In particular, if you simulate for a particular purpose, then going back, looking at how your model had been versus actual outcome, how good the actual fit there?
So that's a great thing about you have choices. So you can upload Excel sheets if you want. You could tune the model to operational data and patterns, or you can upload functions. All of them are possible.
Right. I guess my question is, when you do that, like how good the result versus actual outcome? Like, do you see like really close fit, or there's still a lot of variation for variables like weather that you may not be able to control for?
So based on the data we got from our industry partner, we validated it versus actual production. So that was already one fit. Now, there is a lot more fine-tuning we need to do. One of the challenges in oil and gas is getting hold of good data and having enough analysis to really go to the well level to understand what you can do. So sometimes you need to validate at a higher level, and if we have more data, then we go to well level validation. It depends what's available, and it can be very, very different depending on a company.
Thank you very much for the presentation. somewhat related to an earlier question, but you briefly mentioned that you're calling some external libraries, some external Java libraries and whatnot, and that makes me wonder, did you have to integrate with a reservoir model, physics-based, or first principles-based? And if the answer is no, did you just not feel the need to for now, or was it too difficult? If the answer is yes, can you expand on what kind of communications are going back and forth between the two types of models?
Well, specifically for the reservoir, that's a huge science alone. So we are not modeling the reservoir in our site. So what we do is like, specifically for reservoirs, we are reading the information from outside. And then we also have internal equations to model part of the reservoir behavior. Now, what else are we doing from external libraries' point of view? We are adding certain behaviors from the physics and chemistry. That information is really important for several elements of the system in order to take decisions to what to do inside the model. They really need that information. So yes, we are building our own Java libraries to plug with these simulation models, and then we are also using external resources that we have in order to increase the accuracy of our calculations.
To add to that, reservoir models tend to spit out flat files as a result. Those ones we can read.